In this video, we're going to talk about hyperbolas. It's another one of our conic sections. We'll start with the parametric definition of a hyperbola. The parametric equations of a hyperbola that open right and left are x equals h plus a secant theta, or a secant t, and y equals k plus b times the tangent of t. T goes from 0 to 2 pi. So switching the secant and tangent in our curves here. So if we switched where the secant and tangent are, then it would change from being a hyperbola that opens right and left to one that opens up and down. And we'll take a look at that over here. So to eliminate the parameter, we're going to use a strategy sort of like what we did when we had a sine and a cosine, and we used our favorite trig identity, sine squared plus cosine squared equals 1, but we're going to turn this into an identity involving secants and tangents. So this is going to become sine squared over cosine squared is tangent squared, and cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So if we subtract that tangent squared to the other side, we get secant squared t minus tangent squared t is equal to 1. So this is what we're going to try to do when we eliminate the parameter, is we're going to solve for secant and tangent and try to plug it into this identity. So like we did with sines and cosines, we're going to subtract the h, and that will get us to a secant t is equal to x minus h. We'll divide that a to the other side to isolate the secant t. We'll do the same thing on the other side here with the tangent. So we'll subtract the k to get b tangent of, I didn't write that right, b tangent of t, and then we'll divide the b over. So then we are going to plug these in to this identity that we created. I'm going to slide up a little bit here. So what we're going to get is x minus h over a squared. That's going in for the secant and the secant squared. It's going to be a minus rather than a plus, like we got with the sines and cosines. And then y minus k over b squared is equal to 1. So we will separate, we'll square the numerator and denominator and get x minus h squared over a squared minus the y minus k squared over b squared is equal to 1. So this is going to be our equation of a hyperbola that opens right and left, like we see up here. Now, when we do eliminate the parameter on the greens here, we'll get x minus h is equal to b tangent of t, and x minus h over b is going to be tangent of t, and y minus k is a secant t, and y minus k over a is secant of t. So we'll get y minus k over a squared minus the x minus h over b squared is equal to 1. So we get y minus k squared over a squared minus the x minus h squared over b squared equal to 1. This we're going to try to recognize as a hyperbola that's going to open up and down. So when we look at this, kind of some notable characteristics. As usual, we can see the center, h and k. So that's the translation part that we have seen in pretty much every equation that we have had before. Now, the big thing different than an ellipse is you're going to see a minus sign. Now, you're going to get a squared and a b squared like we saw with the ellipses. But in an ellipse, what makes a squared is that it's bigger. In a hyperbola, that's not necessarily the case. What makes a squared is that it goes with the first term that's positive. that comes before the minus sign. And the b squared term goes with the term that follows the minus sign. In a hyperbola, a squared might be bigger than b squared, it might be less than b squared, it might even be equal to b squared. So that's not what makes it a squared. In an ellipse, we know that a squared is equal to b squared plus c squared, but in hyperbola, we're going to see that it's the c squared, that distance to the focus, that is the largest value, not the a. Okay, let's get a geometric definition of a hyperbola. So a hyperbola is the set of points in a plane such that the absolute value of the difference of the distances to two fixed points is a constant. Whew, that's a lot to digest. It looks something like this. So here, first we have a hyperbola that opens right and left. If you take any point on that curve, then when you look at the absolute value of the distance to one focus minus the distance to the other focus, that is our constant. Okay, and likewise, when you pick any point on a hyperbola that opens up and down, the absolute value of the difference of the distances to the foci is a constant. It's the same for every point that's on this curve. Okay, it's not really very intuitive. Now, we got a bunch of vocabulary that goes with these. A lot of these words are similar or the same as what we used for an ellipse. Sometimes they have slightly different meanings. A is again going to be the distance from the center to a vertex. The vertices are going to be these points that are the closest to the center. So that's one vertex, that's another, and the distance from the center to the vertex, that distance is A. That segment that connects the two vertices is known as the major axis or the transverse axis, and so that's always going to be equal to 2A. The distance from the center to, now we don't, these yellow points here are not really points on the curve, and we'll show you in a moment where they come from and what their significance is. But these are kind of the equivalent of what we would have said was the endpoints of the minor axis. But what we're going to call them here in the case of hyperbola is they're going to be the endpoints of the conjugate axis. So this distance from the center to the endpoint of the conjugate axis, that distance is b. So the distance, that segment that joins the two endpoints of the conjugate axis, is always going to be a length of 2b, much like what we saw with the minor axis and an ellipse. And using the same language we did with ellipses, c is the distance from the center to focus. So that distance there, this distance is c. Now notice that the foci are further away from the center than the vertex. Okay, they're all the way, and this is actually considered the interior of the hyperbola. Okay, so they're going to be further away than the vertices. And so they don't have a name. It's not like a conjugate axis or the major axis. Now, an important idea in hyperbolas are these asymptotes. So the asymptotes are these lines that the hyperbola is going to approach as you get further and further to the right and to the left. It starts to look like two straight lines the further right and further left you get. And so those asymptotes are going to have a slope. Let me switch to red there. The asymptotes are going to have a slope in the case of hyperbola that opens right and left. It's going to be a b over a. But in the case of a hyperbola that opens up and down, the slope this distance to the vertex is going to be our A, and this distance to the conjugate axis is going to be the B, and so the slope in that asymptote is going to be A over B, or a negative A over B. And so that's something to notice. It will, whether it's A over B or B over A, depends on which way the hyperbola opens up. Well, let's look at an example here and kind of talk about what's going on a little bit. So we're going to look at this hyperbola, 9x squared minus 4y squared equals 36. So we know it's going to be a hyperbola because all of our hyperbolas and ellipses and conic sections are not going to have an xy term in them. It's a little more complicated when you have an xy term. But in ours that don't have the xy term, then if there is a x squared and a y squared, then it's either going to be a circle, ellipse, or hyperbola. If the coefficients were the same number and the same sign, that would be a circle. If they were different numbers, but there was a plus, they were the same sign, that would be an ellipse. And if we have an x squared and a y squared, and they are different signs, like we see here, that will make it a hyperbola. So we're going to divide everything by 36. And so that's going to become an x squared over 4 minus y squared over 9 is equal to 1. Let me come back to that in a moment. I'm going to first try to show you why the asymptotes work the way they do. So I'm going to get y by itself. So I'm going to subtract the 9x squared over. So that's going to be a negative 9x squared plus 36. We can divide by negative 4. So we'll get y squared is going to be 9 fourths x squared. And we divide by the negative 4, that'll be a minus 9. Now we're going to square root both sides. So we'll get a positive or a negative. And then I'm going to factor that 9 fourths out. I'm going to leave it in the radical for a moment, but I'm going to factor it out of the terms that are inside that radical. So that's going to give us an x squared. When we divide by when we factor out a 9 fourths, that means divide by 9 fourths, which means multiply by 4 ninths. And so that's going to leave us with a minus 4. Now the square root of two things that are being multiplied, we can write as the square root of their product. So I'm going to pull that 9 fourths out. So that's going to be a plus or minus. The square root of 9 fourths is 3 halves. And then we have the x squared minus 4. Okay, here's where we sit right now. Y is a positive or a negative square root of x. I left off the 3 halves. That was pretty important. 3 halves square root of x squared minus 4. Now, my claim is that as x gets really, really big, as x goes to either positive or negative infinity, as the x gets really, really big and you square it, that's even bigger. Think 1,000 squared, 1,000,000 squared. That minus 4 is very insignificant. The bigger x gets, the less important that is, and the more our square root, our plus or minus 3 halves square root of x squared minus 4 is going to look like plus or minus 3 halves times just the square root of x squared. That is, it's going to look like plus or minus 3 halves x. It's going to look like a straight line through the origin with slope 3 halves and negative 3 halves. So what that means in terms of our graph is this. We can see that our equation, which we're going to put into standard form, but we're going to make the argument that as x gets really, really big, this is going to act like a straight line, either y equals 3 halves x or y equals negative 3/2 x. So the way we're going to graph this is we'll see the center is at 0, 0, because there's no h, the h and k are just 0 and 0. Notice that the slope, the rise, is the square root of 9. So that's the 1, 2, 3, and I'm going to go 3 up and 3 down. The square root of 4 is 2, so I'm going to go 2 right and 2 left. Then I'm going to draw a little rectangle that has these sides that go through those points there. Then from that rectangle, going through the center, I'm going to draw these straight lines that are going to be our asymptotes. And that one is y equals 3/2 x. And the one that goes through the other diagonal is going to be y equals negative 3/2 x. So our actual curve now is going to approach those asymptotes as we go further and further away. Now, turning our attention back to this equation, when we plug in 0 for y, then we get x squared over 4 is equal to 1. If we multiply the 4 to the other side and take the square root, we're going to get positive or negative 2. So that means 2, 0 and negative 2, 0 are going to be points on our hyperbola. Now, if we try to do that for x, if we try to put in 0 for x, we get a negative y squared over 9 equals 1. When we multiply by negative 9, we've got a problem because the square root of a negative is not a real number, which is telling us that our hyperbola does not cross the y-axis. Okay, there's not going to be a point here at these places here. That's just going to be, we're going to use that rectangle to get our asymptotes. Now, we're starting at our vertex here, and we know as we go further and further to the right, then it's going to approach y equals 3/2 x and y equals negative 3/2 x. And so we're going to draw it so it approaches those asymptotes. Likewise, from this vertex, as we go to negative infinity in this direction, our curve is going to approach those asymptotes. And that is how we are going to draw our hyperbola. We'll see another example or two in a moment here. Now we want to find the foci, and the foci are going to satisfy c squared is equal to a squared plus b squared. Truly does look like the Pythagorean theorem. The big thing is the foci, the distance to a focus, is bigger than the distance to the vertex, which is what happens in the case of an ellipse. So we're going to say c squared is equal to, remember, a squared is the one that goes with the positive term, that's the 4, plus the b squared is going to be the one that follows the minus sign. So our c squared is 13, and our c is the square root of 13. The foci always go on that major or transverse axis, the same line that connects the vertices. So square root of 13, we know, is in between square root of 16 and square root of 9, so it's in between 3 and 4. So we're going to count from the center, 1, 2, 3, 4, so somewhere in here is going to be our focus, and that is going to be, where are we, square root of 13, comma 0, and in the other direction, 1, 2, 3, in between 3 and 4 is our other focus, and that's a negative square root of 13, comma 0. All right, a lot to these hyperbolas. Okay, here we go. We're going to try to graph our hyperbola. We're going to label the vertices, the foci, and the asymptotes. So we want to make it equal to 1, so we're going to divide by 100. I'm going to write the positive term first. So this is going to be a y squared over 4 minus an x squared over 25 is equal to 1. So we know that this is centered at 0, 0. In the y direction, we're going to go the square root of 4, so we're going to go up 2, down 2. Since that comes with the positive term, those will actually be vertices. So 0, 2 and 0, negative 2 are the vertices. Now we're going to go in the x direction. The square root of 25 is 5, so I'm going to go 1, 2, 3, 4, 5 in both directions. But I'm not going to plot a point there. I'm just going to use that to draw a rectangle that I'm going to then put in the diagonals as our asymptotes. So it's going through the, you got to kind of use your imagination there. It's going to go through the center and through the corners of our rectangle. Those are going to be the asymptotes. So this is going to be y equals, the slope is going to be a rise of 2 and a run of 5. And since this is centered at the origin, it'll be a y equals 2/5 x. And the other asymptote will be a negative 2/5 x. So our actual hyperbola is going to contain these vertices and will approach those asymptotes. So it's going to open up and down because we had what we would call a y squared over a squared hyperbola. Now to find the foci, we're going to take c squared equals a squared plus b squared. So c squared will be 4 plus 25, that's 29. So we're going to get the square root of 29, and that's in between the square root of 25 and the square root of 36. So our square root of 29 is going to be in between 5 and 6. They're going to lie on that major axis or transverse axis, so we're going to put them on the y-axis. So let's see, we're going to go 1, 2, 3, 4, 5, 6, in between 5 and 6, and that is going to be one of our foci. So that's going to be 0, comma, square root of 29. And we have in the other direction 1, 2, 3, 4, 5, 6. So in between 5 and 6 is going to be 0, negative square root of 29 is our other focus. Okay, I kind of infringed on my space here, so I'm going to slide it over a little bit to create some more room. So we're going to complete the square in x and y. So it's going to be x squared. We have a minus 9y squared plus 36y, and we'll add the 72 to the other side. X squared is okay the way it is. We're going to factor the negative 9 out of those y terms. So that'll make that be a minus 4y. We'll leave a space and get the 72. We're going to take half the middle term, which is 2. Squared is 4. That 4 is going to get multiplied by a negative 9, which is negative 36. So adding the 4 in there is changing the left side by a negative 36. So we'll do the same thing to the other side. So now it's going to look like in factored form, x squared minus 9 times y minus 2 squared over 36. We want to make it equal to 1, so we're going to divide everything by 36. That will get us to x squared over 36 minus y minus 2 squared over 4 is equal to 1. So our hyperbola is going to open right and left. So we're going to go in the x direction. The square root of 36 is 6. 1, 2, 3, 4, 5, 6. So, oops, I'm sorry. I got to put the center in there first. That's going to change things. So our center is at 0, 2. So our center is at 0, 2. That's going to be right there. Now that's not really a point on the curve, but we're going to go from there 6 in the x direction. So we'll go 1, 2, 3, 4, 5, 6. That's going to be right there. That's going to be at the point 6, comma 2. That's one vertex. We'll go 1, 2, 3, 4, 5, 6. That's going to be at negative 6, 2, and that's our second vertex. In the y direction, we're going to go, the square root of 4 is 2. So we'll go up 2 and down 2 and use that to draw our rectangle so that we can then get our asymptotes as the diagonals. So from the center, we're going to go through those corners, and when we label them now, we're going to write them in point slope form. So the center is 0, 2, so it's going to be y minus 2 is equal to the slope, which is a rise of 2 over a run of 6, and I guess 2, 6 we can reduce to 1/3, and that's just x because it's x minus 0. And the other asymptote is going to be y minus 2 equals negative 1/3 x. We can plot our vertices. They're going to be right and left. So one vertex, so we already labeled them. I'm going to make them red now. And then it's going to open right and left. So we're going to approach those asymptotes. And then I guess we better find the foci. So we're going to go c squared equals a squared plus b squared. So c squared is going to be 36 plus 4. C squared is 40. C is going to be the square root of 40, which we'll write as 2 square root of 10, but we'll think of square root of 40 as being in between square root of 36 and square root of 49. So that's going to be in between 6 and 7. So let's see, in the x direction, we're going to start at the center 0, 2. 6 takes us to the vertex, and we have to go 6 and 7 is going to be right there. So that is going to be one focus, which is going to be square root or 2 square root of 10 comma 2. And likewise in the other direction, this is going to be at negative 2 square root of 10 comma 2. Okay, let's see what we can do with this one. So there's a lot going on here. We're going to complete the square in x and y. So we'll gather the y terms together, leave a space, gather the x terms together, and put that constant on the other side. We'll factor out the leading coefficient. So that's going to make that be a 4y. That means we'll factor out that negative, which will make that a minus 2x. And then we'll take half the 4 is 2. 2 squared is 4. And so we'll add the 4 in there. That 4 will get multiplied by 16. And so we're going to add 64 here. Half of 2 is 1. 1 squared is 1. It's going to get multiplied by that negative 1, so we'll subtract 1 there. So now it's looking like 16, y plus 2 squared minus x minus 1 squared. And let's see, negative 1 and negative 47 is negative 48, and negative 48 from 64, I believe, is 16. So we'll divide everything by 16 to make it equal to 1. So that's going to be a y plus 2 squared over 1 minus an x minus 1 squared over 16 equals 1. So I'm going to see how we can start graphing this. Our center is going to be at 1, negative 2. So we'll go 1, negative 2 for the center. In the x direction, we're going to go, in the y direction rather, we're going to go, the square root of 1 is 1, so go up 1 and down 1. So that's going to be a point right there, which is at 1, negative 1. That's going to be one of our vertices. And going down 1 from that, I didn't plan that very good. So our center is at 1, we said negative 2. And our other vertex is going to be at 1, negative 3. And we'll go right and left. The square root of 16 is 4. So 1, 2, 3, 4. And 1, 2, 3, 4. Whoops, 1, 2. So 1, 2, 3, 4 is there. So we'll use this now to draw our rectangle so that we can then get our asymptotes as the diagonals of that rectangle. So we're going to go up this way and that way and here and here. So our asymptotes, we're going to use our point slope form, which we can kind of see right here. So it's going to be y plus 2. Y plus 2 equals the slope, which we went up 1 and over 4. So that'll be a 1/4 times the x minus 1. So there's our point slope form. And the other one will be just the same, except it'll be a negative slope. So negative 1/4. Okay. Our vertex, we said, was right here. And as we go to the far right and left, it's going to approach those asymptotes. So since we had a y squared over a squared hyperbola, it's going to open up and down. We can find our foci by going c squared is a squared plus b squared. So that's going to be 1 plus 16, and that's going to be the square root of 17, which is just a little bit more than the square root of 16, so a little bit more than 4. So we can go from the center, we'll go 1, 2, 3, 4, and then a little bit. So I'm going to put 1, focus is going to be there, which is going to be 1. And then let's see, the y coordinate of that center was negative 2, so it's going to be a negative 2 plus the square root of 17. And then we'll go down a little bit more than 4, so down 1, 2, 3, 4, and a little bit. And so that's going to put our other focus about, well, that didn't work right. Let me try that again. So our other focus is going to be here, which is at 1 comma negative 2 minus the square root of 17. All right, very good. Well, believe it or not, we still got some more to do. Let's see if we can find an equation of a hyperbola that has vertices 2, negative 3, and 2, 1, and slopes of asymptotes plus or minus 3/4. So the vertices are going to give us 3 pieces of information. I'm going to graph it so we can see what this is doing. So 2, negative 3 is going to be there, and 2, 1 will be there. So those are our vertices. Now we know that halfway in between is going to be our center. So that's going to put our center at 2, negative 1. So that's going to give us our HK. We also know that because the vertices are up and down, our hyperbola is going to open up and down, which means it's going to be a y squared over a squared minus x squared over b squared hyperbola rather than an x squared over a squared. And we know this distance from the center to the vertex is a, so we know a is equal to 2. Okay, so now let's use our asymptotes. Now remember, the slope of the asymptote will be different. It'll be either a over b or b over a, depending on whether the hyperbola opens up and down or right and left. Since our hyperbola is opening up and down, this is going to be the A, and so the B is going to be the horizontal. So we're going to get that our slope is A over B. Now we know that the A is 2, so that means we have 3/4 is equal to 2 over B. And so we're going to solve this proportion by cross-multiplying and getting 3B is equal to 8. So B is going to equal 8/3, and we actually need B squared, so that's going to be 64/9. Yuck. Okay, so we said our equation is going to be a y squared over a squared. It's going to be a y minus the y coordinate, we'll make it a y plus 1 squared over a squared, which we said was 4, minus x minus the x coordinate to the center is 2 squared over the b squared, which is 64/9 is equal to 1. Now that would be okay. Probably a better way to do this is to divide by the 64/9 is to multiply by its reciprocal. So a better way would be to write it as 9 times x minus 2 squared over 64 is equal to 1. So this would be our preferred, but you'd still get full credit for the first one. All right, let's try one more of these things. I know this video's getting long. So now, let's see, let's draw. We've got vertices, -1, -1, and 1, 2, 3, 4, 5, -1. So those are our vertices. So it looks like they're 6 apart, so halfway in between. 1, 2, 3, right there is going to be our center, and that center is going to be at 2, -1. Because the center's in between there, our hyperbola is going to have to open right and left, which means it's going to be an x squared over a squared hyperbola. And we know this distance, a, is going to be 3. Okay, now let's see. And because it's opening up and down, if you imagine our asymptote here, the slope of that asymptote is going to be a rise b and a run of a. So our slope is going to be b over a, which means 5, 6 is b over a. And we know the a is, oops, I lost my pen. We know the a we said was 3. So we have 5, 6 equals b over 3. Cross multiplying is going to get us 6b is 15. So b is 15/6, which I guess we can reduce to 5/3. And so our b squared is going to be 25/9. Okay, so here we go. X minus the x coordinate of the center is 2 over the a squared, which we said was going to be 9, minus the y plus 1 squared over 25/9 is equal to 1, or the preferred form would be x minus y squared over 9 minus 9 times y plus 1 squared over 25 is equal to 1. But I'd still accept that other version. Okay, long video. Thanks for hanging in there.